Hello everyone. This lecture provides a systematic overview of energy management systems, covering their fundamental framework and the major classification perspectives. Some key challenges and future research trends will also be discussed at the end of this lecture. An EMS is essentially a decision-making system that schedules the reference output power of distributed energy resources through an optimization framework. Its goal is to ensure that the microgrid operates both economically and securely. We can break EMS decision-making process into three parts: the input, the optimization program, and the output. First, the EMS collects several types of information as inputs: the load and renewable generation profiles, bus voltage measurements, battery charging states, and any scenario-dependent information required by the EMS constraints. The core of the EMS is an optimization program. Here, the objective is usually to minimize the microgrid operation cost. The decision variables are typically the reference power profiles for all dispatchable energy resources of the entire planning horizon, and the decision must satisfy a variety of constraints including power balance, battery limits, voltage limits, branch current limits, frequency requirements, as well as box constraints on all decision variables. Finally, the EMS outputs the reference active power profiles for all dispatchable energy resources in the upcoming execution horizon. This reference will be tracked by the local grid forming or grid following controllers at the device level. Now, let's look at how the EMS actually interacts with the entire microgrid system and coordinates all dispatchable energy resources. The system level EMS acts as the brain of the microgrid. It receives state information from the field and prepares an optimization problem. The EMS first performs power forecasting for unschedulable loads and renewable sources. This forecast determines the uncertainty of the EMS must handle. Based on the forecast results and price information, the EMS solves an optimization program to schedule the reference power for all dispatchable energy resources. The output of the EMS is a set of scheduled reference power profiles, which will be sent to every device level controllers at the beginning of each decision interval. At the device level, each inverter-based resources has its own local controller, typically operating at a much higher decision frequency. Most DERs, such as EV chargers and solar inverters, operate in grid following GFL control mode. They track the EMS reference power and synchronize with the grid voltage. For traditional DC generator DG, the device can switch between GFL mode and when grid connected and grid forming mode when the microgrid becomes islanded. Grid forming mode power sources can establish grid voltage and frequency while delivering power at its designed set point. When the breaker connecting the grid to the main grid opens, the microgrid becomes islanded and the GFM resources must play the grid supporting role to support the grid voltage and frequency. When the breaker is closed under normal operations, the main grid sets the voltage and the frequency. The battery energy storage system, such as Megapack, is another flexible resource. It can operate in both grid following and grid forming modes. Now, let's take a closer look at the hierarchical architecture of EMS from the decision time interval perspective. At the top level, the system level EMS works with relative large time steps, typically from 15 minutes to 1 hour. These reference commands are uploaded each scheduling interval, defining the optimal set points of dispatchable energy resources controllers for the upcoming horizon. A larger step size is a trade-off between computational cost for system-level optimization and the EMS performance. At the device level, each dispatchable energy resources runs its local controller, either in grid following or grid forming mode, with the reference power set by the EMS. The device layer operates with a much shorter decision interval to assign the driving signal to the inverter-based power source gate driver or DC generator governor, typically on the order of milliseconds. This fast inner-loop decision allows DERs to continuously update their outputs and track the EMS reference in real time. In short, a shorter decision interval for device-level controllers enables faster local responses to transient events, while avoiding introducing huge computational burden to the system-level EMS, which is a key advantage of the hierarchical EMS architecture. Here is a review of the EMS workflow. First, we prepare the EMS by building the microgrid model and training the forecasting tools. Next, the EMS monitors key system states such as voltage, battery state of charge, and power measurements. Based on the monitored data, the EMS scheduled the optimal reference power trajectories for all dispatchable energy resources. Then, the scheduled reference powers are dispatched to all device level controllers. Local grid forming or grid following controllers execute these commands by regulating dispatchable energy resources outputs. And finally, the system states are updated and feedback for the next EMS decision cycle. Now let's look at the category of EMS. From the decision frequency perspective, EMS can be classified into day-ahead and MPC classes. The day-ahead EMS makes a one-time optimal scheduling for all dispatchable energy resources based on the forecasts for the next day. Its advantages are no computational burden and good global optimality. However, it's high sensitive to forecast errors and real-time disturbance. Next, the MPC-based EMS performs rolling optimization by frequently updating measurements. It provides strong adaptability to real-time changes, but this comes with a significant higher computational cost. From the operation mode perspective, EMS can be classified into grid-connected and islanded version. In grid-connected mode, the EMS relies on the main grid for voltage, frequency, and power balance. This allows simple convex constraints and the ability to exchange power with the main grid to achieve economical operation. But it only applies to the grid-connected condition and doesn't guarantee secure operation by itself. In islanded mode, the EMS is responsible for maintaining standalone stability without main grid support. It enables reliant operation during outages or emergencies, yet it requires a long convex model and depends on sufficient GFM capacity. For the control structure perspective, EMS can be classified into centralized, distributed, and hierarchical EMS. In centralized EMS, all information and decisions are handled by a single central controller. This structure achieves high optimality but suffers from heavy computational burden and communication requirements. In distributed EMS, decisions are made by multiple local controllers through communication. It's scalable, but its performance relies heavily on effective coordination of each parts. Finally, hierarchical EMS coordinates power scheduling, voltage frequency regulation, and fast local control across different timescalers. It leverages timescaler separation, offering improved stability and flexibility, and is widely used in modern EMS designs. Finally, let's look at some technical challenges and future research trends. First, EMS performance is highly sensitive to forecasting errors, especially for load and renewable generation. To address these challenges, the robust EMS frameworks that explicitly consider uncertainties in load and renewable forecasting is a hot topic research direction. Second, MPC-based EMS requires repeated online optimization, which leads to significant computational burden. Third, many EMS models become non-convex once grid security constraints are included, making the computation expensive, particularly for MPC-based methods. To deal with these issues, second-order co-program relaxed MPC-based EMS provides secure and computationally efficient scheduling, as shown by our recent work. Fourth, increased battery state of charge models and simplified grid security constraints limit EMS decision quality in many applications. Physics-informed data-driven modeling methods provide a possible solution for this issue. Fifth, fixed or rule-based EMS strategies lack generalizability and struggle to adapt to diverse and dynamic operating conditions. Reinforced learning opens the door to adaptive and experience-driven scheduling. Lastly, load and solo forecasting often rely on limited data samples, which further degrades EMS performance. Transfer learning and geographic information based sequence learning can significantly improve prediction accuracy under data scarcity. In the following lectures, we will dive deeper into each component of the EMS framework introduced today and gradually develop the theoretical and practical tools needed to address these issues.